You may have seen one of our initial thermal irradiance examples, and the document associated with that example, where we have a simple mid-wave infrared camera with a chilled detector and a two-element lens, cold stop, of course, to separate the warm from the cool, a sunshade. And the sunshade happens to have a couple of bolts protruding somewhat into the field of view. So we get warm corners on the detector due to thermal irradiance of the bolts, coming from the bolts. I'd like to dive in a little bit further and talk about a question asked by one of our bright young representatives. He said, "How do you know that's what caused it?" And of course, we could philosophize all day about different ways of proving it. We could prove the radiation transfer equation by doing a series of temperatures and seeing how the thermal irradiance changes. And that's a great way to do it. And I might do that in a later edition, a later video. But for now, I thought, let's go very directly at the answer to this question. Basically, how would I have answered that question if I didn't have the thermal irradiance tool to promote or provoke the question being asked? And so I took the same system and I basically said, let's make the bolts radiate into the entrance pupil of the system and see what happens. And so what I did is, to make things particularly interesting and kind of minimalist in the sense that I can separate different parts of the problem and look at them individually, I said, let me use the body, in other words, the cylindrical part of one bolt, as a thermal radiator, and let me use the cap, the flat plane on the end, as another radiator, and do the two bolts separately, but with each one only radiating from one of those two parts. And in that way, see how things differ between the two sides, because we should probably be able to distinguish a little bit of difference. And also, we can see the ray paths directly going to those places on the detector. So you might already say, okay, you've already proven it. What else do you need to do? But let's have a little bit more fun with it. As long as we have an excuse to have fun, let's try to do that. So we have, let's look at a 3D view of it. So of course you see again the body of one bolt radiating, the cap of the other bolt radiating. And in detail, for those of you who are thinking about exactly how you would do this and saying, how did I make just rays going to the entrance pupil happen? Well, we teach this in the class in Stray Light, but it's a straightforward approach. If we make these perfect Lambertian radiators, then they look like black bodies. And if we place the rays just above the surface, pointing towards it instead of away from it, and then we scatter towards, using the towards construct of the scatter model, but we scatter towards the entrance pupil, which of course means that we are scattering to the cold stop with proper imaging through the lenses, and once through the cold stop into the detector area and the cold shield interior. And that's what we've done here. And you even see I did spots position on the detector, and I did spots position on the rays that even went past the detector and hit the back of the cold shield interior. And so I know this is, I'm showing you an outline, so it's not quite as clear as it might be. I can basically take that cold shield interior and turn most of it back on, and then I'll just make the side walls. So now you can see the back of the cold shield, And I'm going to make the detector a solid, and it's kind of hard to see there, but that gives you an idea of what I'm doing. I'm looking at the rays and what they hit back here, particularly the detector and the back of the cold stop interior, that back wall. And so now that I've told you what I've done, let's look at this a little bit more carefully. So this is the trace view. This is the bolt radiation at the detector. And so we see the radiation due to the body of one bolt, the end of the other bolt. And you might say, wow, it looks like the end's radiating more. The spots are a little bit more compact, dense, form a well-defined boundary. That's partly because they're slightly out of focus, and that's partly because this has a well-defined boundary that is entirely within the field of view, whereas this has a boundary that fades out of the field of view and has varying direction and distance slightly. So without getting too hung up on the details, that's at the detector. This is at the cold stop back, so you see the shadow of the detector in the light that got to the cold stop interior back. And now let's look at the energetics of these. So first, the bolt 2 and 3 image at the detector, and you see the body energy here, but the cap energy of the other bolt here is really faint. I can do right-click enhance to turn that up a little bit, but we have a better way of doing that that's a little bit more of a quantitative view. Let's just look in log space and give it 3 decades of dynamic range. And at this point you see a great big peak for the bolt body, lower peak, but nice and smooth for the bolt cap of the other bolt. Now let's do the same thing at the cold shield back. This is the view at the cold shield back. We see the shadow of the detector clearly. We see where the actual geometry of the cold shield ends. And if I do enhance on it, it actually ends up fading out. But never fear, we can go to the log view and we get something that is pretty clear and sensible. And it's almost believable that this is a projected circular plane, but a plane that's at quite an oblique angle that is also slightly out of focus. And in this case, still much higher amplitude than the cap on the opposite side. And going back to the 3D view, I'm going to turn on first radiometry view of the detector, and we can zoom in and actually see that right in its place, the logarithmic view that I showed you a minute ago. And if I turn on the radiometry for the cold shield back, then we see that as well. So I think this is a nice qualitative way of making ourselves believe that the bolt radiation is really what is forming these peaks. And with that, I think it's a fun little thing to look at. There's still a lot we can play with here, but I want to stop talking while you're still listening and come back later with another interesting way of looking at thermal irradiance in ASAP. Thank you very much for your attention.